Okay, welcome everyone to the first talk, SFT Journal Club talk of this year. Our first speaker is Ashoke Sen, and he's going to tell us about the instanton amplitudes. So over to you, Ashoke.
Okay, thank you very much, and thanks for the invitation to speak. So today I'm going to give some general introduction to the instanton amplitudes. Okay, what are the difficulties and how to calculate them? Okay. So let me begin by introducing the problem. Okay. So first, what are the instantons? Okay. So a simple answer is that the instantons are to d branes what ordinary instantons are to solitons in quantum field theory. Action classical solutions in string theory. Okay, just like instantons. Okay, so in this sense, they are different from particles or extended objects which have infinite action. And the significance of the instantons, just like ordinary instantons, is that they generate non-perturbative contribution to string amplitudes of the form e to the minus c over gs, okay, where c is some constant and gs is the string coupling. Okay, so this is the de-instanton action. In fact, as we will see, c is not quite a constant. Okay, but for now, let's just think of this as a constant. Okay, it's independent of the string coupling. Okay, let me put it this way. Oh, I should have said that if you have any questions, please feel free to ask in the middle. Okay. So why are de-instantons important? Okay, so these are important because they are expected to play an important role in many aspects of string phenomenology. For example, they provide contribution to the superpotential that are needed for moduli stabilization, okay, either in KKLT scheme or this large volume scenario scheme. Furthermore, in many cases, one finds that the perturbative contribution to various Yukawa type couplings vanish, okay, and de-instantons provide the leading contribution. Okay, so for example, many of the intersecting brane models, if you want to generate Yukawa couplings between massless particles, okay, then you need the instantons to do that. Okay. And finally, I should add that the instantons are also important for understanding non-perturbative aspects of string theory in general. Okay. And possibly by understanding the instanton contributions fully, we may even get a non-perturbative definition of string theory. Okay, because we know how to give a perturbative, how to compute perturbative amplitudes, and now we know how to compute the instanton amplitudes. So the idea is that perhaps we can put them together to get some full non-perturbative definition of string theory, okay, at least in high enough dimensions where these are the only kinds of non-perturbative contributions which exist.
Sorry, just a question. Could you comment about what you're saying, thinking about NS5 brane? Because they should give a different kind of contribution.
Yeah. So that's why I said if you are in a high enough dimension, okay, that means if the number of non-compact dimensions is high enough, then the NS5 branes don't contribute, right? Because NS5 branes, in order for them to produce a finite action, they have to wrap 6 compact directions.
Okay, thanks.
So type to be in 10 dimension, for example, right? You don't expect NS5 brane contributions to NS5 branes to contribute significantly in the amplitudes. But in low enough dimensions, you are certainly right that you need NS5 branes also.
Okay, thanks.
Okay, now one key feature can in principle be calculated systematically using perturbative worldsheet methods. And so the general structure of a de-instanton amplitude has this form. You have e to the minus c over gs. This is a standard factor that accompanies all instanton contribution. Okay. And then this is multiplied by sum over worldsheets that includes those with boundaries. Okay. So the relevant perturbative string theory that describes this sum over that is needed for computing the sum over worldsheets is the theory of open strings on de-instanton and closed strings. Now the problem of implementing this, carrying out this sum over worldsheets, okay, is that open strings on de-instantons carry zero momentum along non-compact directions. Okay. And that's simply because of the fact that we are imposing Dirichlet boundary condition on all the non-compact directions. Okay, so there is no momentum in those directions. Okay. And this means that the usual technique of analytic continuation and momentum that one uses to get finite amplitudes in string theory no longer works. Okay. Because the momenta are fixed. Okay. In fact, they are strictly zero along the compact directions, along the non-compact directions. And of course, along the compact directions, they are quantized. Okay. So let me illustrate this by an example. Okay. So here is the simplest string amplitude, the Venezian amplitude in bosonic string theory. Okay. It's given as a single integral. And physically, this gives a 3-level scattering amplitude of 4 tachyons in open string theory in alpha prime equal to 1 unit. Okay. And the pi is the external momentum. Now, if you look at this, you can see that this diverges. This is the divergence near the y equal to 0 end, okay, or 2p2.p3 is less than -1. That's the divergence from the y equal to 1 end. And the conventional viewpoint that one takes for this is that we define the amplitude in the regime where you can define these integrals, and then analytically continue to the other kinematic regions. Okay. And in the case of this 4-point amplitude, this can be implemented manifestly by writing this in terms of the ratios of gamma functions. Okay. But more generally, this is the procedure that one follows, that we use the method of analytic continuation in defining amplitudes. Okay. But clearly, this would not have been possible if momenta are fixed at a value where the integral diverges. Okay. Imagine that the momentas, for some reason, were fixed at 2p1.p2 equal to -2 and 2p2.p3 equal to -3. Okay. In that case, okay, you cannot continuously vary the momenta. Okay, you may not even know this expression as a function of these. Okay, you know it only for those spatial values. Okay, and then it's not clear what to do with this integral. Okay, there is no analytic continuation that is possible, and this is a kind of problem that. So our strategy will be to use string field theory to deal with the divergences that arise in the worldsheet theory. Okay. So let me just say a few words about what string field theory is. Okay. So string field theory is a regular quantum field theory with infinite number of fields, okay, essentially one for each string mode. Okay. The perturbative amplitudes are just some more Feynman diagrams because this is a regular quantum field theory. Okay. But this is a particular special kind of field theory. Okay. And these are the property that each Feynman diagram, the contribution from each Feynman diagram can be expressed, okay, can be rewritten as an integral of the form that appears in the worldsheet description of the amplitude. Okay. So each Feynman diagram can be expressed as an integral of this form. Okay. Except okay, that the integral covers only part of the integration region over the worldsheet variables, okay, which more generally are moduli spaces, are variables that parameterize moduli space of Riemann surfaces and locations of vertex operators. Okay. So for example, in the case of Venezian amplitude, if you try to represent this as a contribution in string field theory, okay, it will be divided into 3 segments. Okay. One, a small segment near y equal to 0, then a small segment near y equal to 1, and then a small segment that interpolates between the missing region, that covers the missing region. Okay. And these you can reinterpret as a contribution from the S-channel Feynman diagram, T-channel Feynman diagram, and contact Feynman diagram. Okay, that's the way string field theory works. Okay. But otherwise, string field theory is just a way to rewrite the string perturbation theory as quantum field theory amplitudes. So now let me describe why it helps in solving divergences. Okay. So the general strategy that one follows, okay, in making use of string field theory, okay, is to first we write down the worldsheet expression for a given amplitude, okay, even if the integral is divergent. Okay, just like the Venezian amplitude, okay, that even if 2p1.p2 is less than -1 and this is less than -1, we still write down this integral anyway. Okay. Then we reinterpret this, okay, as coming from a string field theory path integral or sum over string field theory Feynman diagrams. Okay, you can use one or the other depending on convenience, okay, or depending on what kind of problem we are dealing with. Okay. Once you do that, okay, then you try to find the origin of the divergence from the perspective of string field theory. Okay. And once you understand why the divergence, okay, then we can resolve it using insights from quantum field theory. Okay. Because in quantum field theory, we know how to resolve divergences. Okay. In fact, the only kind of divergence that we, in principle, have difficulty with in quantum field theory are ultraviolet divergences. Okay. So, for example, if the quantum field theory is not renormalizable, you don't know what to do with ultraviolet divergences. Okay. But those ultraviolet divergences are absent in string theory anyway. Okay. So, in particular, in the language of string field theory, the ultraviolet divergences will be absent because the vortices have exponential suppression factors for large momentum, for large Euclidean momentum. Okay. So, it's not the ultraviolet divergences that bother us in string theory. Okay. But it's more the infrared kind of divergences that we have to deal with. Okay. And those you can deal with by using insights from quantum field theory. Okay. And this is the procedure that we'll be using. Okay. So far, string field theory techniques have been applied to 3 classes of examples. Okay. And these 3 classes of examples have been chosen because the answer is known from a dual description. So the first class of examples is 2-dimensional bosonic string theory. Here the result is known from the matrix model. It was initiated by this Harvard group. And the matrix model result was in fact known long ago from the work of Moore, Plesser and Ramgoolam in the 90s. The second class of examples where it has been applied to a d-instanton contribution to type 2b string theory amplitudes in 10 dimensions. Here again, the result, the actual answer was known from application of S duality and supersymmetry. Okay. Again, it was known since the late 90s. Okay, starting with the work of Green and Gutperle, and then Green and Sethi essentially gave a proof. Once they showed that once you assume supersymmetry and S duality, okay, then we can predict what the answers will be. But of course, we want to approach the problem by not using S duality, but by direct computation. The third class of examples where this has been applied are d-instanton contribution to type 2A or type 2B string theory on Calabi-Yau 3-folds. Okay. And here the result is known again from a dual description. Okay, from not dual description, from the use of duality and mirror symmetry and supersymmetry. Okay, so this is much more involved. Okay. And this, in fact, is the work done in the last 10 years. Okay, by various authors. Okay. But the upshot is that here again, that there is a definite prediction of what the d-instanton contribution should be for a particular class of amplitudes in these theories. Okay. And we find that the string field theory technique works in all cases. Okay. And given this, okay, for the cases where the answer is not known. Okay, and I'll discuss some of these cases at the very end. Okay, so this finishes the introduction. So now let me give some more details of how you go about analyzing d-instanton amplitudes. So as I said, the d-instanton amplitude has an overall factor of e to the minus c over gs. Okay, and then it's given by sum over worldsheet. Okay, just like normal string theory. Okay, and as in normal string theory, the worldsheet amplitudes are proportional to gs, the string coupling, to the power minus the Euler number of the worldsheet. Okay. So because of this factor, okay, we can see that once you have decided that you will deal with the d-instanton amplitudes and you have fixed this e to the minus c over gs factor, okay, then the worldsheet contribution can be organized, okay, by the Euler number that they carry. Okay, and the leading contribution, okay, will come from maximizing the Euler number, because you want to get as many negative powers of G string as possible. Okay, so you have to maximize the Euler number. Okay, and that you can easily convince yourself, comes from essentially product of disk amplitudes times the exponential of the annulus. So let me explain this. Okay. So why product of disk amplitudes? Okay. Because disk has Euler number 1. Okay. So you have to basically use as many disks as you can. Okay. But of course, disk, you have to have one insertion, okay, on the disk. So if you have certain number of closed string vortex operators, a certain amplitude that you are trying to compute, okay, the idea is that for each of those closed string vortex operators, you choose one disk and you insert the closed string vortex operator on the disk. Okay. So that's the way you maximize the number of disks. Okay. And then the annulus, of course, has chi equal to 0. Okay. So putting in an annulus, okay, doesn't gain in the power of coupling, but you also don't lose any power of coupling. Okay. So this means that at any given order in the loop expansion, in the GS expansion, okay, you have to allow arbitrary number of insertions of annulus. Okay. So you can choose not to insert an annulus, or you can choose to insert one annulus or two annulus and so on. Okay. And so these can be resummed into something called the exponential of the annulus amplitude. Okay. And so these, all the diagrams in this have the same power of G string. Okay. In particular, GS to the minus the number of closed string vortex operators that you have. And that's the leading contribution. Okay. And one point to note here is that normally we don't include disconnected worldsheet. Okay. Because typically disconnected worldsheet has the feature that each worldsheet has separate momentum conservation. Okay. But this is not the case here because we use Dirichlet boundary condition at the boundaries, okay, which means you break from any other contribution, okay? Because as you will see, the momentum conservation will be implemented at the very end. Okay, so that's why you have to include disconnected worldsheet in this sum over worldsheet, sum over genus. Okay. Now at this order, okay, these all give finite contributions. Okay, you don't have to use string field theory. You can in fact evaluate these just by using the worldsheet methods. Okay, standard worldsheet computation. Okay. So all the subtleties, okay, are in the exponential of the annulus diagram. Okay, because this is where the divergences of the kind that I was talking about come in. Okay, and we'll see explicitly where the divergences are. So physically, this exponential of the annulus, okay, can be thought of as a one loop determinant of fluctuation of string fields around the instanton. So here is the general structure of the annulus amplitude. Okay. So this is the parameter T that is basically the modular parameter of the annulus, okay, which you can think of as a ratio, okay, of the circumference to the width of the annulus. Okay. So T goes to infinity means that the annulus circumference becomes long. Okay. That's what is also conventionally called the open string channel. Okay. So this trace is taken over all the open string states. Okay. But we take the trace over all the open string states which are annihilated by B0. Okay. This, the reason that you have to restrict to only B0 equal to 0 states is because there are ghost zero modes. So these B and C are the usual BC ghosts. Okay. So because of the ghost zero modes, okay, unless you restrict to, unless you observe the ghost zero modes explicitly, okay, you will get 0 essentially from this trace. Okay, because you are calculating this trace weighted by -1 to the f, where f is a space-time formula number. Okay, so you have to put this B0 equal to 0 condition. Okay, otherwise you have this e to the -2 pi I T L0, okay, times -1 to the f, where f is a space-time formula number. Okay. And here I should say that in the case of superstrings, this trace runs over GSO even open string states. Okay. And there is a subtle factor of 2 in the Ramon sector that I'll describe later, okay, which we'll see encounter later as we proceed. Okay, but roughly you can think of this as the structure of the annulus. Okay. Now, this has the possibility of divergence from the t equal to 0 end and t equal to infinity end. Okay. But in fact, if you have a consistent string theory without closed string tachyons, okay, then one can argue that the integrand is finite as t goes to 0. Okay. Because t goes to 0 is a closed string channel, okay, and there is no divergence in the closed string channel as long as tachyons are absent. Okay, the massless particles can be present, but the massless part, this is low because you are talking about d instantons. Okay, it's low enough dimension, so the massless particles really don't give divergences. Okay, because see, d instantons, the closed strings on the d instantons carry momentum in all directions. Okay, so you have a large momentum integration in the numerator. Okay, it's ddk, where d is the number of non-compact dimensions. Okay, and as long as d is larger than 2, okay, we are fine. Okay, there is no divergence from the closed string channel. Okay, so you expect that there is no divergence from the closed string channel. Okay, so then once you know that there is no divergence, what you can do is that you can put a lower cutoff, okay, epsilon, to this integral, and then take the limit epsilon goes to 0 at the end. Okay, and in that process, okay, once you have put this lower cutoff epsilon, you can deal with each of these terms in the trace separately. Okay. So if you write it this way, okay, this trace, if you write as sum over bosons of e to the minus 2 pi t hb minus sum over fermions of e to the minus 2 pi t hf, okay, these are the conformal weights of the bosonic and the fermionic states. These are space-time bosons and space-time fermions. Okay. Then you can easily convince yourself that once you put this epsilon here, okay, you can change variable, you can do this integral easily, and you get an expression like this. And this is true. Yes, go ahead, please.
So did you say that the annulus contribution is from fluctuation around the instantons? Is that what you said?
That's right, yes.
So
from
how
the
do you
boundary,
treat, okay, so then how do you treat the corrective coordinates of the instantons, such as space-time positions of the instantons? Do
yes,
you
so
integrate over?
We'll see that, see, they are already hidden here. Okay, so you have to separate them out and then do the integral separately.
So you're going to subtract the contribution from corrective coordinates? That
That's
can
right,
be,
yes.
okay.
Exactly.
Thank you.
Okay. But at this stage, this is just a formal expression. Okay. See, from the worldsheet perspective, right? You don't see any collective coordinates directly. You are supposed to calculate annulus and that's it. That's what it is. Okay. But we will see that this already knows about the collective coordinates. Okay. And once you rewrite in the language of string field theory, okay, collective coordinates will emerge automatically.
Okay. Thank you.
Okay. Okay, so if you now take the exponential of this, you get the square root of product of HF over product of HB. Okay. And this is true as long as HB and HF are positive. Okay. So this is the same equation I have written again. Okay. So as long as HB and HF are positive, then there is no problem. Everything is an identity, what I have written. Okay. If HB happens to be negative, then the original integral is ill-defined. Okay, why is it ill-defined? Because you can clearly see if HB is negative, then this blows up as C goes to infinity. Okay, but this side is well-defined. Okay, this is in fact analytic continuation. Okay, there is an ambiguity here whether to choose a plus sign or a minus sign. If HB is negative, right, then there is a natural sign here. Okay, but that in fact is fixed once you understand it in the language of string field theory. Okay, you have to choose the steepest descent contour and that fixes the sign automatically. But the problematic cases are the ones where either HB or HF vanishes. Because if HB or HF vanish, you can see from here that that's a logarithmical divergent integral from the t goes to infinity end. Okay, so it's clear that this integral diverges. Okay, and that's what you see here. Okay, you get 0 by 0 form, which is not very easy to deal with. Okay. So here we follow the strategy that I outlined. Okay. So the remedy will be that we will try to regard this as path integral over open string fields and then try to make sense of the integral. Okay. And here I should just say that when I say path integral over open string fields, okay, these are not really fields because open string fields live in zero space-time dimensions. They are living on d instanton. Right? And so they don't carry any momentum. Okay. Which means that when you take the Fourier transform, they don't have any space-time coordinate. They are really zero-dimensional field theories. Okay. So when you talk about the path integral over open string fields, these are really ordinary integrals. Okay, not even quantum mechanics. There is ordinary integration over ordinary variables. Okay, and that's what you have to perform. Okay. So we are now going to focus on a particular example. So we'll illustrate this procedure with the example of a single instanton amplitude in type 2A string theory on Calabi-Yau manifolds. Okay, and this is the based on the work that with Sergei Alexandrov and Bogdan Stefanski. Okay. But I should just say that the same procedure works for multi-instanton amplitudes and also in the other theories. Okay, and I'll mention these briefly at the end. Okay. Now, if we further focus, since we are focusing on type 2 on Calabi-Yau manifolds, okay, let me just say that in type 2 on Calabi-Yau manifolds, the only supersymmetric instantons are Euclidean D2 branes wrapped on 3 cycles in the Calabi-Yau threefold. Okay. And here I should note that a Euclidean D2 brane is actually a 3-dimensional object, right? Because you call normally a D2 brane, okay, it has 2 spatial and 1 time direction that are tangential. But a Euclidean D brane has 3 Euclidean directions. Okay. So a D2 brane has 3-dimensional world. Okay. So when you say a D2 brane, okay, the instanton is really that it's localized in time, okay, and it's wrapping a 3 cycle inside the Calabi-Yau. Okay. So as I said, the first task for computing any amplitude is e to the a. Okay, because this multiplies any amplitude. Okay, just like this e to the minus c over gs is a universal factor. Okay, e to the a is also a universal factor because you can always add arbitrary amount of annulus for any amplitude. Okay, so this is what you have to compute first. Okay, and once you have computed this, you can use the same result for any amplitude induced by this t instanton. Okay, supersymmetric, non-supersymmetric, it doesn't matter. Okay, so here is the expression for the annulus. Okay, it's a difference between the contribution from the Neveu-Schwarz and the Ramond sector. Now, one can argue on general grounds that for D2 branes on supersymmetric 3 cycles, these two are actually equal. Okay, this we can show by supersymmetry. Okay. Now, the fact that these two are equal, okay, doesn't mean that A is 0. Okay, and it doesn't mean A equal to 0 for the reason that I mentioned earlier. Okay, but it does show something that is useful. Okay, what it shows is that for the L0 positive states, okay, so when you expand this fns and fr in parts of e to the 2 pi minus 2 pi h b or a minus 2 pi h f, okay, then for L0 positive states, okay, namely for hb and hf positive, okay, then we can see that there is exact cancellation between the bosonic and harmonic contributions. Okay, so you don't have to worry about those. Okay, we can just forget about them. Okay, but because that cancellation you can trust. Okay, so you have to focus our attention on the hb equal to 0 or hf equal to 0 states. Okay, the states for which the controllers vanish. Okay, because here, as we saw, okay, even though it looks like 0 minus 0 in the exponent, okay, in terms of the actual contribution to the A, it's really 0 by 0. Okay, and that's ambiguous. Okay, and you have to understand what that means.
Just a question, because yes, what you are saying is true if you can commute the sum of a state with the integral, because if you first perform the sum of the state, the two f's cancel. You can get some problems if you flip the integral with the sum of the states. Otherwise, I cannot see whether you get.
Yeah. Okay. So we'll see. I mean, that's why. Let me just finish this transparency, and then it will become clear. Okay, that how we can flip. Okay, I think this is what I've said here. Okay, so what we are going to do, okay, to deal with this 0 by 0 problem. Okay, and as Igor just pointed out, that it's a question of whether you do the integral first or the sum over state first. Okay, so we'll first modify this problem a little bit. Okay, by putting slightly shifted boundary condition on the two boundaries of the annulus. Okay. So in other words, let's imagine that on the two boundaries of the annulus, instead of fixing them at the same space-time position, okay, we just displace them a little bit. Okay. Eventually, we'll set that displacement to 0. Okay. This will make it easier to deal with this problem. Okay. So this basically adds a small constant h to the L0 eigenvalues. Okay. And this doesn't break conformal and BRST invariance on the worldsheet. Okay, so you can trust this, that you are not breaking any symmetry. Okay. And once you do that, okay, then these integrals are finite. Okay, because now you have only positive e to the minus 2 pi h ht. Okay, the lower end we have already seen there is no divergence, so you can put a explicit lower cut of epsilon here, okay, which you take to 0 at the end. Okay, and now we can carry out the same manipulation that we had done earlier. Okay. And we'll see that everything is consistent. You will get 1 equal to 1. Okay, there will be no issue here. Okay, I hope this answers your question, that this is the way we are going to deal with this. Okay, and this makes it clear what exactly is going wrong. Okay, when you take h goes to 0. Okay, so once you make this deformation, okay, then we don't have 0 anymore. Okay, so here what I have written at the contribution to the what would have been the 0 h equal to 0 states. Okay, massive states cancelled anyway, so that I have removed. Okay, and what you find is that for h, once you add a small shift in h, okay, it's actually 2 minus 2. Okay, what it was earlier that there are contribution of 2 from the Nebuchadnezzar sector and 2 from the Ramon sector. Okay, so this FNS was 2 and FR was 2. Okay, if we just ignore the massive mode contribution. Okay, and the 2 minus 2 has now become 2 e to the minus 2 pi th minus 2 e to the minus 2 pi th. Okay, so it's really 0. Okay, so nothing much has happened. Okay. Now I am going to rewrite this even further. Okay, trivial rewriting. I write it as 4 minus 2 minus 2. Okay, so basically what I am doing here is the Nebuchadnezzar sector, this 2, I am writing as 4 minus 2, again for reason that will become clear in the next slide. In fact, in the next slide. Okay, because this has direct interpretation in terms of string field. Okay, how these contributions are coming from, where these contributions are coming from in string field. Okay. So now if you calculate e to the a, okay, I'll get by using the previous formula. Okay, these 2 minus 2s will give you h squared times h squared, and then h to the 4 comes from this 4. Okay. Again, nothing has changed, right? I'm writing 1 equal to 1. Okay. But now the idea is that this factor here, okay, I can reinterpret this, okay, as an integral. Okay. In fact, this I could have done even at this stage. Okay, when I first showed you the square root of hb over hf over hb. Okay, at this stage itself, I could have said that I could rewrite this as a path integral. These are like path integral over fermions, which give contribution in the numerator. These are the path integral over bosons, which give contribution in the denominator. Right? That's the way string field theory reproduces this answer. Okay, and that's what I'm doing here. Okay, except that I have just eliminated all the massive string modes. Okay, to make life simple, because their contribution cancels anyway. Okay, so now this 4, okay, 1 over square root of h to the 4 comes from integration over 4 bosonic modes, okay, which I'm calling xi mu. Okay. The h square that comes here, okay, that's the h square that came by splitting this 2 as 4 minus 2. Okay, this is still a Nebuchadnezzar sector contribution. Okay. This comes from integration over a pair of Grassmann odd modes, okay, PQ, okay, with weighted by e to the action is e to the minus HB. Okay. The action for xi mu is minus h xi mu xi. Okay. And then we have 4 Grassmann odd variables. These are coming from the Ramon sector. Okay. And their action in string field theory is given by half G alpha beta chi beta. Okay. Where G is an antisymmetric 4 by 4 Hermitian matrix, which satisfies the G square is equal to h times I. Okay. Now, one point to notice here is that the eigenvalues here, okay, the eigenvalues of the quadratic operator here, okay, is square root of h, okay, while eigenvalues of the quadratic operator, where the quadratic term here is h, Okay. So this difference comes because in the Nebuchadnezzar sector, okay, the kinetic operator is actually L0 in string field theory. Okay. Whereas in the Ramon sector, the kinetic operator is G0. Okay, that's the square root of L0. Okay, that's why the eigenvalues are square root of H. Okay, that's this factor of half that I was talking about earlier. Okay, here actually the number of modes is twice. Okay, not 2 modes. Okay, to get -2, you need 4 modes. Okay, whereas here to get 4, I only needed 4 bosonic modes. Okay, so now here we come to the collective modes. Okay, so the xi mu's will be the 4 Grassmann even modes. Okay, and you can easily identify in string field theory what these modes are. Okay, and you can easily show that these are related to d instanton position. Okay. This PQ will be again 2 modes that are coming in string field theory from the Nebuchadnezzar sector. Okay, but these are Grassmann odd modes. Okay, and those represent ghost fields. Okay, these are in fact the ghosts that arise from gauge fixing. Okay. And we will see this explicitly how these ghosts arise actually out of gauge fixing. Okay. And the chi alphas are the 4 Grassmann odd modes. They represent fermionic 0 modes. Okay. Again, these you can identify by looking at string field theory. Okay. And eventually, when you take the H goes to 0 limit, okay, the xi mu's will become the 4 collective coordinates. Okay, the 4 bosonic collective coordinates that you have to integrate over. Okay. Chi alphas will become the 4 fermionic collective coordinates associated with broken supersymmetry, because the instanton breaks half of the space-time supersymmetries. Okay. So you see that the annulus amplitude actually already knows about the existence of xi alpha and chi alpha, xi mu and chi alpha. Okay. Because once you write the annulus in terms of string field theory path integral, the collective mode integral is already there. Okay. These are the problematic ones. Okay. The Grassmann odd modes, these are, as I said, they represent ghosts. Okay. And we will see how to deal with those. Okay. They are not collective modes in any sense. Okay. And in fact, they are the ones that are responsible for singularity in gauge fixing. Okay, as you will see. Okay. Are there any questions at this stage?
Sorry, I didn't quite understand what you mean by preserving the cohort invariance and BRST invariance by this deformation. Could you explain a little bit more about this?
Yeah, because it's still a perfectly CFT. It satisfies all the axioms of CFT, right?
But did you change the spectrum by hand?
Yeah, I just added a constant H to the spectrum into all the L0s, right? But you can also get this spectrum, the same spectrum that I'm using here, right? If you just take 2 boundaries and put a shifted H at one end, okay, a shifted position, you will get exactly this spectrum.
I see. So is this consistent with the OPE also?
Yeah, it is consistent with OPE. You can think of this, it's as if instead of having the 2 boundaries lying on the same instanton, right? The 2 boundaries, as if the 2 boundaries are lying on slightly shifted instantons, which is also perfect physical configuration, right?
Okay. But I'm a little bit confused because so it is kind of like going to the Coulomb branch in the argument extension value to the okay. So then how do you modify the ghost sector? I'm a little bit confused about this. If you change the boundary
modify the ghost sector. Okay, even also in the ghost sector, it just adds this H. Because you're just adding a twist. See, if you imagine a string that is stretched between 2 D branes, right? Okay. That open string gets an overall tension, contribution from the tension. Okay. But the oscillators are exactly the same.
I see.
Okay, so there will be no change in the oscillator sector. Okay. You just get a little contribution from the tension.
Okay, yeah.
Of this open string.
So how about ghost sector?
It's the same. So the ghost sector, the ghost oscillators are acting on the ground state, right? Okay. The ground state has gotten this extra H contribution to the L0.
Okay, that's what you did by hand, right?
Exactly, yeah.
Okay.
By hand meaning it will come out automatically if you actually calculate the spectrum of open strings that are stretched between 2 D branes.
I see. Yeah, I think I need to think about this, but thank you.
Yeah, so I mean, you can think of it another way, that if you take a pair of these D strings, right? Then the spectrum of open strings going from one D string to another D string is identical to the spectrum of open strings going from the one D string to the same D string. Okay, as long as the D strings are coincident. Okay. So when you calculate the annulus partition function, instead of calculating the annulus partition function for open strings with both ends lying on the same D string, D instanton, you imagine that you are calculating the annulus partition function for open strings with ends on two different D instantons. Okay, coincident. They are physically identical. And now I'm saying that let's just pull one of the D instanton a little away. Yeah, that's what I'm doing.
Okay. So then I'm not sure what it doesn't seem to affect the ghost sector. So that's I'm confusing.
Yeah, it will affect the ghost sector because all the oscillators are acting on a ground state, right?
Yeah.
Okay. So the ground state energy has gotten shifted by H. So oscillators are identical.
Okay. I see.
Right. See, imagine that you have a very large open string, right? Then clearly you cannot have any state of that open string that has low energy. Right. So whether you act with ghost oscillators or matter oscillators, right? That energy coming from the tension must be there.
Okay.
Right. And that's what is being added.
Okay. Yeah.
Okay. But string field theory action we'll see will be a little more complicated. Right. When you do this.
Okay. Yeah.
Okay. Well, I'll write down the string field theory action in the massless sector. Right? And we'll see the structure there. What happens.
Okay. Yeah.
Okay, but eventually, of course, we are going to take H equal to 0, right? This is just to show how the worldsheet result can be reinterpreted as a string field theory result. Okay,
yeah.
So we are not going to use non-zero H in our calculation.
Yeah, this is just to interpret the origin of this factor.
Exactly, yeah. This is just to show that the worldsheet contribution can be reinterpreted as a string field theory possibility.
Okay. Thank you.
Okay, and it's easier to do that as long as the H is there, right? Because then you can do these manipulations without any ambiguity. Because the point is that with H equal to 0, you cannot do these manipulations anyway, right? That's why you need string field theory. Okay, but it's good to see that the two answers are the same. Okay, when things are supposed to work, right? And that is when H is non-zero. Okay, we are trying to show that this answer and the string field theory answer are the same. Okay. So for that, of course, you have to still see that this action comes out of string field theory. Okay, and we'll see that how it comes. Is that okay? Are there other questions? Okay, so let me summarize what you are going to find. Okay, and then I'll write down the some of the equations explicitly. Okay. So what you find is that this e to the a can be interpreted as a single gauge fixed path integral of open string field theory on the instanton. Okay. In other words, these integrals are just the integrals over the string fields. Okay. In fact, restrict to the massless sector, because the massive sector cancels anyway. So in this interpretation, the modes P and Q will represent Fourier-Popov ghosts. Okay, and they are the Fourier-Popov ghosts that come from this gauge fixing. And now this clearly shows that the single gauge must be becoming singular in the H goes to 0 limit. Okay, because if these are Fourier-Popov ghosts, okay, then H goes to 0 limit means that the ghost kinetic term is vanishing. Okay, but vanishing of the ghost kinetic term is a clear signal that the gauge fixing procedure is breaking down. And you will see explicitly how this happens. Okay, but you can just guess from here. Once you say that P and Q are the ghost fields of gauge fixing, then that H goes to 0 is indicating a singular gauge choice. Okay. So the remedy that will follow will be to work with the original gauge invariant path integral before gauge fixing. Okay. And this will get rid of the zero modes P and Q from the integral, okay, and then land us on the collective coordinate integration, collective mode integration.
Okay, you are just considering just the one instanton sector because you haven't the matrix structure. So exactly.
Yes, exactly. I'll mention briefly the multi-instanton case at the end.
Because if you would consider the n instanton sector, you could get massive of diagonal states, and these shouldn't give any issue, while the diagonal state should still have the problem you are talking about, isn't it?
Yeah, in fact, the massive states will never give any issue. Right? It's the massless off diagonal and diagonal states which will be the problematic ones.
Yes, okay. So in any case, you have always the massless diagonal states in any sector, and so these are the source of all issues in any case, and so it is worth.
Massless diagonal and off diagonal states.
Yes, but the off diagonal can be made massive if you move the instantons apart from each other, the center of mass.
Yeah, but see, the point is that you have to integrate over the coordinates of the instantons, right?
Yes.
So you cannot really move them away at will. I mean, the integral will do what it does, right? And you have to see where the major contribution is coming from.
Okay.
And in fact, the contribution actually comes from coincident instantons.
Yes, yes. When from zero size and when they are overlapped. Yes, but
yeah. So that's where the actual contribution will come from.
Yes. Okay.
Okay. So now here I have written down the gauge invariant path integral. Okay. So this is very similar to what you saw earlier. Okay. What is the difference? That first of all, there is a BC integration over PQ. Okay. Instead, there is an integral over this mode phi, okay, which is an additional mode, okay, which you get when you don't fix single gauge. Okay, so this is what is called a classical string field. Okay, PQ are the ghost states, okay, which are not classical string field. But if you are starting with the gauge invariant formalism, okay, then you have integration over the classical fields and you divide by the volume of the gauge group. Then you carry out further gauge fixing to get the ghosts. Okay. So this is the original gauge invariant form of the path integral. Okay. So this phi mode, okay, if you are considering bosonic string theory, this is the this would be the state that C0 acting on the vacuum. Okay, that state is projected out in the single gauge, but in gauge invariant form of string field theory, that state will be there. Okay, in superstring, there is an analog of this. This is the integration over the string field theory gauge transformation parameter in the massless sector. Okay. So this essentially multiplies the vacuum state. Okay. So what is S? Okay, we can calculate S from the known form of string field theory action. Okay, see here is the result for S that you find. Okay, which is given here. It's again very similar to what we had earlier. In fact, if you set phi equal to 0, okay, this becomes exactly identical to what we had earlier. Okay. But you see that here, okay, one point you see that Xi3 is spatial, right? I mean, you have broken somehow the rotational symmetry along the transverse directions. Okay. And that's because this string field theory action, okay, I have written down in a background, okay, where the two boundaries have been shifted in the 3 direction. Okay. So this is where explicitly we see what the structure of the string field theory action is. Okay, because you have shifted the two boundaries in the 3 direction. Okay. But of course, in the h goes to 0 limit, you recover the full symmetry, right? As h goes to 0, you can see that you recover the full symmetry in all transverse directions. So what is theta? Theta is a string field theory gauge transformation parameter. Okay. And from the known form of gauge transformation laws in string field theory, you can figure out how phi and Xi3 transforms. Okay. And here are the transformation laws. Okay. And you can easily verify that under this transformation, this is invariant. Single gauge, okay, in this language corresponds to setting phi equal to 0. Okay. And as you can see that for H non-zero, that's a perfectly legal gauge choice because phi does transform under gauge transformation. Okay. So when you set phi equal to 0, okay, then this you can set phi equal to 0 here, you get back the original action. Okay. Theta integral is gone because you have gauge fixed. Okay. And the other thing you see that there is a determinant factor, right? You have to change variable from theta to phi. Okay. So you get a Jacobian, which is H. Okay. And it's this H that you reinterpret as Faddeev ghost integral. Okay. That's this integral. If you see the integral over P and Q, okay, weighted by minus H e to the minus HPQ gives you exactly H. Okay. So if you start from this gauge invariant path integral and carry out the usual Faddeev procedure, you get back the integral that you started with. Is this point clear? Okay. But now you see from here that if H is 0, then this is actually a singular gauge choice, right? Phi doesn't transform if you set H equal to 0. So you cannot trust this, the gauge fixed version of this path integral for H equal to 0. Okay. But you can trust the original version. Okay. There is nothing wrong with the original version for H equal to 0. And that's what we'll do. Okay. We'll take this form of the path integral and then just set H equal to 0. Okay, so here it is. Okay. You see now that the phi integral becomes a Gaussian. That it doesn't make sense to set phi equal to 0 because phi, shift of phi is not a gauge symmetry anywhere. Okay. In fact, nothing transforms under gauge transformation here. Okay. So you do the phi integral explicitly because it's a Gaussian integral. Okay. And write it to the A as this ratio. Okay. So you have extracted out the collective coordinate integrations, as you can see from here. Okay. But these are not quite collective coordinates yet. You have to normalize them properly. Okay. So the idea now is that we'll have to first relate the xi mu's to the instanton position x mu, okay, and theta to the U1 gauge, rigid U1 gauge transformation parameter alpha. Okay. I'll explain what this rigid U1 gauge transformation parameter is. So first, let's see how to relate xi mu and x mu. So this we find by comparing two results. First, we compute the coupling of xi mu to a general amplitude. Okay, so imagine that you have a disk amplitude with multiple flow string insertion, and you want to now insert another xi mu. So you just multiply by the xi mu vortex operator and integrate along the boundary. Okay, this is the xi mu vortex operator. Okay. And also you multiply by the open string coupling, which I'm calling GO. Okay, this is related to the open string, the tension of the brain by this factor, or the instanton action by this factor. Okay. So you insert this, okay, and then this integral can be easily done by using contour deformation. Okay. This just picks up the residues at the poles, okay, of del x mu, and we get an answer like this. Okay. So the idea is that you have to compare this with the expected coupling of actual instanton position. Okay. And that, of course, will appear via the e to the IP dot x factor. Okay. If P is the total momentum of the closed strings in the amplitude, okay, then the x dependence should be e to the IP dot x, which you can expand out. Okay. And now you can compare the xi coupling with the x coupling to figure out the relationship between xi and x. Okay. So that's what we see here. Xi mu is given by x mu over GO times pi root 2. And so the integral over xi mu, we can now convert to integral over x mu. Now the gauge transformation parameter theta that we saw, okay, that in fact is related to what we call the rigid U1 gauge transformation parameter alpha on the D instanton. Okay. So what is rigid U1? Okay. So imagine that we have the D instanton and we have taken open string whose one end is on the D instanton. Okay, other end can be on some other plane. Okay, another D instanton or some other plane. Okay. Then there is a U1 symmetry. Okay, that just multiplies such an open string state by e to the I alpha. Okay? This is the standard U1 that lives on any D plane. Okay, except that for the D instanton, there is no U1 gauge field. Okay? But the gauge symmetry is still there. Okay, it's not gauge, it's not local anymore, right? rigid symmetry. Okay. So the idea now is that we take this transformation law. So the expected transformation law of an open string with one end of the d instanton and another end on something else, okay, is a multiplication by e to the I alpha. Okay, or for small alpha, it's multiplication by 1 plus I alpha. Okay. And then you compare it with the gauge transformation of the same open string state under the open string gauge transformation parameter theta. Okay. Where the open string gauge transformation laws are known. Okay, so you can calculate what that transformation is. Okay. And then you just compare. Okay. And this comparison gives the relation theta is 2 alpha over g open. Okay. And using this, you can calculate the theta integral, okay, as 2 over g open times integral d alpha. Okay. And you can see from this normalization that alpha has period 2 pi. Okay. So the integral over d alpha just gives you 4 pi. Okay. So you are left with 4 pi over g open. Okay. So you are now going to use these two relations and substitute in this integral. Okay. So after you do that, you get an expression for e to the a of this form. Okay. Here I have written in terms of g open, but g open can be related to the g string. Okay. But it's easiest to relate it directly to the action of the d instanton, right, which you know how to calculate independently. Okay, so these integrals, okay, so x mu are the instanton positions. Chi alphas, as I have already said, these are the harmonic zero mode that are associated with broken supersymmetry. Okay, so these integrals will have to be done at the end, okay, just like the collective coordinates of instantons. Okay, and the reason is that the other worldsheet components also have x mu and chi alpha dependence. Okay, and hence we have to do these integrals at the end. Okay, before we so you shouldn't do these integrals before we have, for example, combine this with all the disk amplitudes. Okay. So eventually, after you multiply this by the disk amplitudes, okay, and carry out the x mu integral, okay, because the x dependence is through this e to the I p dot x factor, the x mu integral will generate this momentum conserving delta function. Okay. So you see that even though here individual worldsheets don't have momentum conservation, okay, it comes at the end after you integrate over the collective mode of the instanton. Now, chi alphas are Grassmann odd variables. Okay. So these integrals will vanish, okay, unless there are at least 4 insertions of chi alpha in the rest of the amplitude. Okay. And those chi alpha integrals will generate a factor of epsilon over 4 factorial that multiplies the product of these amplitudes with these chi insertions, with the vertex of pulse of chi insertions. So this gives a full explicit okay. The important point is this normalization factor that we have extracted out here. Okay. So now I'm going to compare the prediction that came from S duality and mirror symmetry with what we have found. Okay. So for this, let's first try to understand what is it that we are trying to compare. Okay. So it turns out the type 2 on Calabi-Yau has 2 kinds of moduli fields, okay, which can be divided into vector multiplets and hypermultiplets. Okay. And it's a general property of supersymmetry that the moduli space factorizes. Okay. And where it factorizes to all orders in perturbation theory and including non-perturbative corrections. Okay. Supersymmetry prevents the mixing. Okay. Now it turns out that the dilaton, okay, which controls the string coupling, is in the hypermultiplet. And this immediately says that the vector multiplet moduli space that is computed at the tree level is exact. Okay. Because the corrections can only depend on the string coupling, but string coupling is in the hypermultiplet. Okay. So there cannot be any correction to the vector multiplet moduli space. Okay. But the metric on the hypermultiplet moduli space actually receives perturbative and instanton contributions. Okay. And these have been predicted, as I said, by this work of last 10 years. Okay. The correction to the hypermultiplet moduli space, d instantons, have been predicted by combining inputs from supersymmetry, mirror symmetry, and S duality. And now the question that you want to address is, does this agree with the direct computation? So for this, let me just say a few words about hypermultiple moduli space metric. So this is a general form that I've written. Okay. So at tree level and loop order, you have some known form of the hypermultiple moduli space metric. Okay. And the correction from a wrapped Euclidean D-brane on a cycle gamma. Okay, this, as I've already said, the relevant D-branes are D2 branes wrapped on 3 cycles for type 2A. Okay. Imagine that T gamma is the action, okay, which includes this 1 over GS factor. Okay. So that correction takes this form. Okay. You have this overall factor that gives a d-instanton suppression. Okay. And then the correction takes this form of a perfect square. Okay. In fact, I should say here that when originally the corrections were computed, okay, in these papers, okay, it was not written in this form. Okay, it was written in a more complicated form. Okay. By doing the instanton contribution explicitly, we discovered that the correction must take this form. Okay, otherwise it cannot be matched with the instanton correction. And then you went back to the formula that existed from the duality analysis definitions to actually bring it into this form, right? We showed that we found that we can actually bring it into this form after some field definition. Anyway, so the upshot is that the S duality, mirror symmetry, and supersymmetry already gives a prediction for what these numbers are. Okay. And now you have to see how to compute this directly from string computation. Okay. Now, the metric, of course, enters the scalar field action. Okay. But the problem is that the string theory doesn't calculate the action directly. Right? What string theory calculates unambiguously is the amplitude. Okay. So what we need to do is to see what amplitude is affected by these corrections, okay, and then compare that amplitude with the amplitude computed in string field theory. Okay. So it's clear from this that the first effect of these corrections, okay, will appear in the 4-5 scattering amplitude. Okay, in fact, it will be proportional to the Riemann tensor computed from this metric, okay, and it appears in the 4-5 scattering amplitude. Now, why 4-5? Okay. One can easily convince oneself that on-shell 2-point and 3-point amplitudes vanish even for complex external momentum. Okay, it's true for scalars. It's not necessarily true for spinors and tensors, but at least for scalars, okay, one can easily check that on-shell 2 and 3-point amplitudes actually vanish. Okay, which have derivatives. Well, yeah, these are derivative couplings. Okay, so you have to go to 4-point amplitude. Okay. So this is the relevant diagram that you have to compute. Okay, exponential of the annulus and then the 4 disks. Okay, with 4 of the scalar vortex operators inserted at the centers. And recall that you have the 4 Fermion 0 modes that you have to insert. Okay, and it turns out that the relevant contribution, okay, that you want, right, 2 derivative corrections, okay, to the amplitude. Okay, they come from inserting 2 0 modes on one of the disks and 2 0 modes on the other of the disks, and having no 0 mode insertions here. Okay, that's the way the 4 0 modes have to be distributed. Okay, and the reason is clear. Imagine that you insert all 0 modes on the same disk. Okay, then these have no powers of momentum. Okay, these are the single scalars inserted at the center. These don't give any power of momentum. You may get 2 powers of momentum, okay, but it will be 2 powers of momentum of the same scalar, right? And then because these are on shell, okay, by p square equal to 0, the result must vanish. Okay. So you need 2 powers of momentum, but the 2 powers must be distributed over 2 different disks. Okay. So that leaves you the only option of inserting 2 0 modes here and 2 0 modes there. Okay. And then you manipulate this expression. Okay, so this is the amplitude, 4 Fermion amplitude. You compare this with the 4 scalar amplitude that is predicted by this correction. Okay, and you have to massage that expression a little bit. Okay, but at the end of it, what you can show, okay, and this is the simplicity of the result. Okay, then up to this normalization factor, okay, this e to the a by 2. Okay, e to the a by 2, because e to the a has to be distributed into these 2 disks as e to the a by 2 here and e to the a by 2 there. Okay. Up to this normalization factor, a gamma m that you saw, okay, is directly given by the disk amplitude with 1 phi m and 2 open string 0 modes. Okay. So even though we have this diagram in mind, okay, the actual computation that we have to do at the end, okay, is just a single disk amplitude, okay, with 1 closed string insertion and 2 open string 0 mode insertion. Okay. That gives you directly this quantity A gamma n. Okay. And this is non-zero. I told you earlier that the scalar one-point function should vanish. Okay. But the reason that this is non-zero is because we don't use momentum conservation, right? Single disk amplitudes, we don't use momentum conservation. Okay, and there it can be non-zero. Okay, it's just some term proportional to PV on this disk. Okay, other questions on this? Okay, so let me now say a few words about how we actually compute this A gamma n. Okay, because after all, you have a Calabi-Yau compactification, right? So how do you do any calculation there? Okay. The way we do this calculation is by taking the large volume limit of Calabi-Yau. Okay. And this limit, in fact, is exact in type 2A because the size modulus is in the vector multiplet, and that cannot affect the metric on the hypermultiplet. Okay, again, because of the factorization between the hypermultiplet and the vector multiplet. Okay. And this I've already said, only relevant D branes are D2 branes wrapped on 3 cycles. Okay. So the way you do this calculation, because you are allowed to take the large volume limit, okay, without losing any generality, okay, we pretend that the D2 brane is locally flat, okay, which is a good approximation of the large volume limit. Then you evaluate the contribution to the amplitude from a local patch of the D brane using flat space vortex operators. Okay, we just use flat space vortex operators of metric to form dilaton and the Ramon form, and do some standard string calculation to find the local patch axis. So then this result, okay, has to be multiplied by the wave function of the external state, okay, and then integrated over the cycle that the D brane runs. Okay. And here the Calabi-Yau geometry becomes important. Okay, because what do you mean by wave function of the external state? Okay, for example, suppose you are trying to calculate the complex structure. Okay, dependence on the complex structure. Okay, we know that the complex structure deformation induces certain deformation of the metric. Okay. Okay. That has to be multiplied, okay, with the corresponding amplitude, okay, the metric amplitude on the D brane. Okay, and that provides the integrand on a local patch of the D brane, and that you have to then integrate over the whole volume of the D brane. Okay. This, in a sense, is the non-trivial part of the calculation that involves Calabi-Yau geometry. Okay. This part of the calculation is just flat space calculation. Okay. But these integrals can be done, and at the end, it gives exact agreement to the predicted result. Okay. So here I have just listed the examples of some of the Calabi-Yau manipulations that we encountered. Okay, so for example, you need these covariantly constant spinors. Okay, why? Because the fermion 0 modes that we insert, okay, their wave function, okay, on the Calabi-Yau is given by the covariantly constant spinors inside the Calabi-Yau. Okay, so those are needed. Okay, these gamma matrices arise from the D brane calculation. Okay, so when you calculate the amplitudes of various vortex operators on the D brane, for example, the Ramon vortex operators will produce gamma matrices. Okay. So you need identities of this kind. Okay. Omega here is a scalar form, and this is as the volume form on the Calabi-Yau. Okay. Here are the examples of some integrals that we encounter in type 2A theory. Okay. Here C3 is the Ramon 3 form potential. Gamma is some Lagrangian 3 cycle of the Calabi-Yau. Those are the supersymmetric cycles. Okay. And you can see that this integral is topological because you are integrating a 3 form over a 3 cycle. So this is easy. Okay. But here you have to perform a Hodge dual, which depends on the metric. Okay. And then you have to integrate over the 3 cycle. Okay. So this integral, for example, will depend not only on the Ramon 3 form potential, but also on the metric through the complex structure. Okay. Here is even a more complicated integral. You take the convolution of the complex structure of the Calabi-Yau with Ramon 3 form. Okay. And then you integrate over this cycle. Okay. But as I said, with some effort, all of these integrals can be done and expressed in terms of the moduli of the hypermultiplet moduli space. Okay, the parameters of the hypermultiplet moduli space and that gives the result that I mentioned. Now, similar analysis can also be done for type 2B string theory, compactification, Calabi-Yau threefolds. Okay. Here it's more complicated. There are 4 kinds of instantons: D-1, D1 on 2 cycle, D3 on 4 cycles, and D5 on the whole Calabi-Yau. Okay. We do work in a large volume limit, even though it's not exact. Okay, so it's an approximate result that we get here. Okay, but we follow exactly the same strategy, and this reproduces the earlier prediction in the large volume limit. Okay, now let me say a few words. Questions up to this point? Okay, so how do you deal with k instantons? Okay, so open strings now carry k by k Chan pattern factors. Okay, so the first few steps are similar to what we did. Okay, you have to unfix the Siegel gauge. Okay, so which means you have now k square extra 5 modes. Okay, because there are k square open string states. Okay, so you have to integrate over all of these k square 5 modes. Okay, so you get this 2 root 2 pi to the power k square. Okay, and now you have to also divide by the volume of the UK gauge group instead of just a U1. Okay, that has to be put in. You have to find a relationship between the gauge transformation, the string field theory gauge transformation parameters and the U1 gauge transformation parameters as usual, the rigid UK gauge transformation parameters as usual. Okay, so all those can be done as before. After you do that initial part, okay, then comes the hard part because you have to do the integral now. So the center of mass part factors out, okay, and that can be treated as in the case of a single instant. Okay, the only difference is you get some powers of k, okay, because of the center of mass weight factor has a 1 over k, etc. Okay, those can be taken care of. Okay, but the rest of the integral gives a supersymmetric matrix integral. Okay, because you have both fermions in the adjoint of SUK, U1 part has been factored out. So you have fermions in the adjoint of SUK and also bosons in the adjoint of SUK. Okay. The question is, how do you deal with this integral, the supersymmetric matrix integral? Okay. So what supersymmetric matrix integral you get? Okay, that's also easy to state. Okay. It's in fact precisely what you get by dimensional reduction of n equal to 1 supersymmetric SUK Young-Mills from 4 dimensions to 0 dimension. Okay. So you write down the Lagrangian of the n equal to 1 supersymmetric SUK Young-Mills, okay, and then take all the fields to be independent of all space-time coordinates. Okay. You get a matrix action. Okay. That's the action that you have to use. Okay. And you now perform integration over those corresponding variables. This is a hard integral, but it turns out that it has fortunately been computed in the 90s already. Okay, with some answers, but perhaps it's not mathematically rigorous, but the answer is already given. Okay, in fact, it was first predicted in this paper, and then it was computed by localization in this paper by Moore, Nekrasov, and Sagasvili. Okay, so you just have to, so the hard part of the calculation is already done, so you just have to lift the result from that paper, okay, and put it back here. This amplitude calculation, okay, and that in fact remains more or less the same, except for some powers of k that you get from trace over Chan factors. Okay. So after you put these results together, you exactly reproduce the predicted result for the k instanton amplitude. Are there questions? Okay, so now let me briefly mention the other cases. Okay. So as I said, the same method works for other cases as well. Okay. What changes is the actual number of bosonic and fermionic collective groups. Okay. But the procedure for gauge unfixing, the Siegel gauge, is universal. Okay. We always get extra Gaussian integration over the phi mode in the numerator. Okay. And you have to divide by the volume of the gauge group in the denominator. And for 2-dimensional string theory, there is also an extra complication because you have a tachyonic open string mode on the D instanton. Okay. So tachyonic mode means that the action has e to the minus m squared times some xi squared. Okay. And so to deal with that, we have to use the steepest descent contour. Okay. So we deal with the tachyonic mode, okay, just as we do a normal saddle point analysis, that we find the steepest descent contour, okay, which means that you have to essentially integrate along the imaginary axis instead of the real axis. Okay, and you do this integral, and that lands you exactly on the right answer, okay, which was predicted from the matrix model analysis. Okay, and this, as I said, also fixes the sign of the term. Okay, I told you earlier that if you have a negative mode, you get square root of that, okay, from analytic continuation. Okay, but that square root of a negative number, okay, has a sign ambiguity. That sign ambiguity also gets fixed by this appropriate choice of the steepest descent contour. So the result is completely unambiguous. Okay, finally, the unknown territory, okay, where the answer is not known. Okay, and that's the case of n equal to 1 supersymmetric compactification. Okay, so if you take type 2 or type 2b on Calabi-Yau threefold and take an orient default, okay, we get n equal to 1 supersymmetric theory in D equal to 4. Okay, and here de-instanton corrections are known to generate superpotential, which is absent in perturbation theory. Okay, of course, perturbation theory does generate some superpotential, but de-instanton corrections generates the kind of superpotential that you don't see in perturbation theory. Okay. And the idea is that using the same technique that we have described, one should be able to calculate the instanton generated superpotential. Okay. Here, of course, there is no known answer from duality that you can compare with. Okay. So you have to just trust the analysis. Okay. And this is some work that is in progress with various authors, okay, my old collaborators, Sergey and Bogdar, and then 3 new collaborators, Sarel, Atakan, and Manki. Okay, so this is still work in progress, and hopefully you will see some results soon. Okay. So finally, I have one concluding slide. Okay. So what I have tried to argue is that string field theory gives a systematic procedure for computing perturbative and de-instanton contribution to the amplitudes. Okay. And we should be able to apply this procedure to calculate de-instanton contribution in situations where S duality may not be of help. Okay, I have already mentioned one case before. Okay. And perhaps also to find non-perturbative definition of string theory by researchers. Okay, because as I said, that at least in high dimension, when the NS5 contributions are absent, okay, then de-instantons are the only non-perturbative contributions that are known to us. Okay. And then we have the perturbative contribution. Okay. String theory gives you a systematic way to do the full expansion, perturbation series expansion, as well as the full perturbation series expansion along de-instantons. Okay. And the idea is that can we combine these to actually get a non-perturbative definition of string theory. So with this, I'll stop. Thank you.
Okay, let us first thank Ashoke for this wonderful talk. So we still have plenty of time left. So if people have questions, please go ahead and ask.
I have a curiosity and a question. I start from the curiosity. What about doing the same computation on a linear background? I'm thinking about this because the coupling constant would change according to the place in the space-time. So
on the linear dilaton background, you mean?
Yes, linear background, linear dilaton background, yes.
Yeah, see, linear dilaton background, of course, this two-dimensional string theory procedure that I described. Right? Let me go back. This two-dimensional string theory, in fact, does have linear dilaton. Right? Because there's a Liouville. It's Liouville plus the free field. So it works quite well even in this case.
Okay, but in the region where the string coupling constant, the dilaton, the string coupling constant is very large, it should be,
yes,
there should be some
so you sitting in that position, right? I mean, we have no choice of where the instanton is in the Liouville direction, right? It will try to minimize its action. And it goes and sits in the highest coupling region. But nevertheless, we know exact description of the instantons in Liouville theory. Right? These are these ZZ branes. And that's what we use.
Okay. Okay. Mm-hmm. Fine.
So typically, if you have a linear dilaton, then in the place where the coupling is large, right, there has to be some cutoff. And in the Liouville theory, it's the tachyon which cuts it off.
Okay. The other point was a question about the integration of a theta variable you wrote. It seems that the theta variable is from 0 to 2 pi, and this I missed why. It is
oh, not theta variable, is the alpha variable which was from 0 to 2 pi. Let me go back.
Because
yeah. You see, the point is that let me move this thing.
Because I thought, okay, you think of U1, but in the previous slide, you said it was associated with a kind of a translation of a regularization of the boundary, and so I thought that you could translate the boundary in whichever place of R4, and so this is the point.
No, this is not a translation of the. Okay, it's theta is the gauge transformation parameter of string field, right?
Yes.
Now you're talking about when h is 0. Okay, a single D instanton. Theta is still a gauge transformation parameter of that theory. Okay, and you know how theta acts on the various fields, right? In particular, if you have an open string that is hanging from the D instanton to a neighboring D instanton or another D plane, okay, we have the gauge transformation laws of open string field theory to find out how theta acts on that state. On the other hand, U1, okay, I have defined it such that that state gets multiplied by e to the I alpha. Okay. So you compare the U1 gauge transformation by alpha and the theta gauge transformation of the same state, okay, and equate them. Okay. That determines the relationship between theta and alpha, which is given here.
Okay, so it's
and now the point is that alpha has period 2 pi. That's how we have defined, right? Because you are picking up a phase of e to the I alpha. So clearly for alpha equal to 2 pi, this is 1.
This from that formula it was clear, but I was thinking about the previous interpretation as
well, it's not really translation, because the previous interpretation is Xi3 is getting translated, but phi is also changing, right?
Mm-hmm.
Okay, when they are separated. Okay, so it's a complicated transformation here.
Okay.
Okay, it leaves the if only Xi3 was translated, then action will change. Right? It's not that. It's it's a symmetry.
Yes, okay.
And for h equal to 0, nothing translates, as you can see. Right? Okay. And that's, I mean, the reason is clear that if we have a single D instanton, right? And if you have an open string that is beginning and ending on the same D instanton, then it shouldn't transform under this theta gauge transform, of the DGD1. Okay, that's why all fields have vanishing transformation for h equal to 0.
Okay, now I understand better. Thanks.
Thanks.
Other questions, comments?
Ashok, can you hear me?
Yeah, I can hear you.
Oh, wonderful. So yeah, I had a question about these resurgence you're mentioning. So normally we would expect that we get from research, we get some information about instanton contributions coming from purely perturbation theory. But here you seem to actually use instanton contributions to get further information. That's something I was.
Yeah, I mean, here you have more information than just perturbation theory.
Yeah.
Right. And so the idea is that if the perturbation theory is not Borel sum, there is ambiguity.
Mm-hmm.
But that ambiguity perhaps you can already resolve because we already know some information about the instanton amplitudes.
Okay.
Right? That's the idea. That I mean, you have more information, and hopefully, I mean, using this, you can resolve all the possible ambiguities that may appear in perturbation theory by trying to read some perturbation theory.
Okay, I see. And should there be some trace of this in the alpha prime limit?
In the alpha prime going to zero limit in the gauge theory?
Yeah.
Yeah, I'm not sure actually because you work in type 2B string theory in 10 dimensions.
Mm-hmm.
That space, right? I mean, you can take alpha prime going to zero limit, but it's not even gauge theory. It's
right. So okay, so it's maybe not easy to recognize.
And the point is that if you really want to go to 4 dimensions, right, then the NS fibrils come in. Because NS fibrils can wrap the compact directions.
Mm-hmm.
Right? And then things become much more complicated.
Yeah.
The NS fibrils are hard to understand. At least so far, they have not been understood in this way.
Yeah. All right. Thank you. Yeah,
this is just a wishful thinking. I don't know whether it will succeed, but at least the point you have more information than just perturbation theory. Right? And it's a systematic procedure. You can generate the whole perturbation series, the GS expansion around any given D instanton. So that's in principle a lot of information.
Yeah, some sort of like summing up the instantons now, so a bit like in Seiberg-Witten kind of thing.
Yeah.
All right. Yeah, that's interesting. Thanks.
So may I ask a question?
Yes, sure.
In the case of multiple instantons,
yes.
Did you say you treated an integration of a relative position of instantons by the hard calculation of a supersymmetric matrix integral or something? Is that what you said?
Yeah.
So I thought that when some of the instantons coincide, there might be additional zero modes. But those complicated things can be taken care of by this supersymmetric matrix integral.
Yes, exactly. Yeah.
Okay.
So those are already part of this matrix, these models, right? So when the D instantons coincide, you will get the whole matrix valued zero modes, right?
Mm-hmm.
And those are all part of this gauge theory, the dimensional reduction of this gauge theory.
I see. So this is so you, in a sense, you can separate this kind of different issues by string theory, worldsheet perspective, right? I thought this is very difficult in general because this kind of so if you really think, take care of this kind of modular space of instantons, it seems to be, I think it is in general a difficult problem. But in a sense, you can separate this different problem from the in a generic situation.
Yeah. I think the point is, see, these integrals, I mean, in the old days, people did the calculation because they are trying to calculate the index of D0 brane bound states.
Mm-hmm.
And they really, for a theory which is a dimensional reduction from 10 to 0,
yep,
because that's where the D0 brane bound state spectrum comes in. But they, in that process, they said, okay, you can also do these.
Mm-hmm.
So these, in fact, did come from modularized space of instantons, right? Because they are trying to understand how to calculate the index over this modularized space of instantons.
Mm-hmm.
So it's not unrelated that, I mean, you are doing integration over modularized space of instantons using this matrix model.
I see. I see. Okay. I see. Thank you. But in a sense, you have to take care of the Jacobian for the change of variables from, in a sense, string field theory variable to the this kind of space-time variables.
Exactly.
Like,
yeah, and that you already know because string field theory action you can calculate, right? And space-time variable action you can calculate.
Yes.
And if you are doing a G-string expansion, right, the change of variable is just some constant factors.
Yes.
Okay,
Just
which
like
involves
the relation between theta and alpha, right?
Exactly. Yeah. Just like the relation between theta and alpha, you have to relate the string field theory variables, the xi mu's, and just as xi mu's and x mu's are related, right?
Yeah. So
and a similar thing has to be done here. So those give factors of G, the open string coupling, some factors of powers of root 2 and powers of pi, etc.
I see.
So all those are needed to get this match.
I see. But for example, I think it's difficult to see the periodicity in the theta variable, right? From string field theory perspective, right?
Yes. So directly from string field theory perspective, it's difficult.
So it is
either that you compare the infinitesimal transformations under theta and under alpha. You calculate the relative normalization and then you translate the integral to alpha.
Yeah. So I think that's a very nice, very good point. But I'm very impressed. Thank you.
Thanks. So typically what happens when you try to go to higher orders in the string coupling expansion, these relations get corrected. Both the relation between xi and x as well as the theta and alpha will get corrected. So you have to do it systematically.
But are you saying you can still do that systematically by this?
Yeah, you can do that systematically, right?
I see. Yeah.
But it requires what? Basically, you know the full string field theory gauge transformation laws, right? Even at the nonlinear level. And you know the alpha transformation laws. So we can still do it. We can do it systematically, but you have to do some work. Because the string field theory gauge transformation parameters, you have to expand in parts of fields.
Yeah.
And you have to keep track of all the parts of fields.
I see.
But in principle, there's no obstruction to doing this. That, in fact, my paper last December, not this December, but last year in 2020 December, there I did extended the analysis to one higher order. Okay, the relation between theta and alpha, for example, and the relation between xi and x had to extend to one higher order in G string.
I see. Okay, thank you very much.
Thank you.
Okay, I think if there are no further questions, let us thank Ashoke once again.
Okay, thank you very much.